All right, well, here we are at our last official lecture. We're going to finish up external memory today. Last time, we started looking at external memory. And we had these parameters. And we started to analyze algorithms purely in terms of the number of block accesses that were needed in order to execute the algorithm. And we tried to develop ways to arrange the data layout so that we could keep that number of block accesses small as we proceeded. And we looked at a few things. We looked at matrix products. We looked at linked lists. At the end, we talked about search trees. Today, we're going to talk about sorting. So how might we sort using external memory? Well, one obvious thing to do is to take one of our standard sorting algorithms and use it in external memory. But what's going to happen if we do that? What kind of runtimes might we expect if we took one of our favorite sorting algorithms, like, say, quicksort, and just sort of ran it in the obvious way? Yeah? It's going to be n log n, right? We already know how to analyze quicksort, right? But of course, now our time now refers to the number of blocks that we read, right? So is it really going to be n log n? How many blocks are we going to read as we're performing this quicksort? Are we going to read n blocks? Yeah?
N over b log n over b?
So it's n over b, right? Because that n in quicksort comes from scanning through all the items in order to split them at the pivot. And now scanning those n items is going to cost us n over b block reads if we store the items contiguously, right? Now, what about this log n over here? When does the recursion bottom out? Well, in standard quicksort, it bottoms out when you're down to a single item, right? But in our external memory model, things get easy sooner. Yeah?
So it should just be log n over b because what you want to do sub-block size b will just have an actual.
Exactly. Once your recursive subproblem is of size b, right, you can read that whole thing in, and it just costs you 1, and then you write it out sorted, right? So the obvious quicksort algorithm has this runtime, okay? The question is whether we can do better, okay? And there's already one sort of significant sign that we should be able to do better, which is that m does not appear in this time bound, right? This algorithm takes the same amount of time no matter if you have 3 blocks or 1,000,000 blocks. So we're not exploiting memory, right? So what other approaches might we consider? Well, what about tree sort, right? So one of the ways you can sort in a standard model is to insert all of your items into a binary search tree, and then they're sorted, right? What would the analog be in external memory? Well, we wouldn't want to use a standard binary search tree because those don't make sense in external memory. But we could use a B tree, right? How long would that take? Well, we have to insert n items, and doing a B tree insert takes log base b of n time. Right, so this is actually worse than quick sorting. Right? In tree sort, we don't have the opportunity to do a lot of the work by scanning through the items. Right? A scan is a very good way to use your time in external memory, because you do one read and you get B items that you want to deal with. There's nothing like that in the B tree, so that kills us. Okay. So it turns out that we want something else. I'm going to head there by thinking about merge sort. What's the runtime for merge sort going to be? Well, unsurprisingly, given that it has the same recurrence as quicksort, it's also going to have the same runtime as quicksort. And so again, it's not making any good use of memory. Right? So how could we make use of memory if we think about merge sort? Right? It doesn't seem like merge sort uses much memory at all, right? We take a pair of sorted sequences and we merge them, and we really just need a couple of units of memory in order to, right? If you think about how you would do a merge sort, right? You'd read in the front block of each list, and you'd sort of combine them to write out the first block of the output list, and then you'd read some more blocks as you needed to, right? So we're not using any memory. How could we use memory? Yes? Good. So this suggests that we could at least turn this n over b into some kind of n over m, right? Because, right, if you can read m items into memory all at once, you can sort them for free once they're in memory, right? You don't have to go down all the way to the b blocks. Okay. So that would give us a little bit of improvement based on large memory, but it turns out we can do a lot better. And we're going to be using actually the same sort of insight as we do with B trees, which is that in traditional computation, it tends to make sense to sort of branch into two, right? Binary search trees and so forth. Divide and conquer recurrences break things into two pieces. But when you've got these big blocks and all of this memory to play around with, it often makes sense to divide up into more pieces right away. Okay, so a good merge sort, or external memory merge sort, does an m over b way merge as its basic operation, which is then applied recursively. Okay, so it takes m over b lists in, and it does that quickly. So why m over b, and how do we do an m over b way merge? Those both have the same answer. Yes?
So m over b is the amount of blocks I can fit into my memory.
Yes. And so how do I take advantage of that?
And so I take advantage of that by basically, I can always keep, like, because how long my lists are, right? But I always only need the head of the list.
Exactly.
And then I can always compare all of the heads at the same time.
I keep the first block of each list in memory. That first block of each list gets consumed to generate output blocks. And I fetch a new block for a list when the previous one is exhausted. Okay, so it's a completely natural generalization of the standard two-way merge, but we're taking advantage of the memory that we have. Right? Since we can afford to keep M over B different lists, we do so in order to get the maximum branching factor, which will make our recurrence more shallow. Okay? Now, the other question to ask is, what is our base case? Right? So again, in standard merge sort, we start with sorted lists of length 1. Right? And then we combine them into lists of 2 and 4 and so on and so forth. What is the correct starting point for an external memory merge sort? Sorry? Okay, so we can read one block into memory at cost 1 and sort it and write it back out, right? So certainly we can start with B, but I claim we can actually start bigger. Yes? Exactly. The base case is n items, is m items. Right? If you want to sort m items, well, you read them in, right? And you sort them. And the cost is just the reading in, because the computational work is free in this model. Okay? So, you combine those two things, that we're working with a base case of size m items, and what you find is that your runtime is order. Actually, let me write out the recurrence for you. Time to sort n items is equal to, well, the basic scanning of those items, plus that's the m-way, that's the merge. Right? Doing a merge is linear in the number of items that you're merging. And then there's the recurrence. I'm going to have m over b of these, and I'm going to need to recurse on things of size m over b smaller. Okay. And as we just discussed, we could actually go all the way down to size m. However, when you solve this, you find out that you get a running time of n over b times the log base m over b of n over b. So I'm writing this as a b here, even though I could write an m. And the reason is that everything is now nicely in terms of b, and because this is in the base of the log, it doesn't actually matter whether I put an m or a b here. It's asymptotically the same, since I'm working base m over b in the base. Okay. So if we compare this to our naive approaches, the difference is that we have this base, right? So we're basically speeding things up by a factor of log m over b compared to the naive algorithms. And again, if you think about standard memory sizes, right? 32 gigabytes, right? And a block size of a few thousand perhaps, or more, right? This is really meaningful in practice, okay? And I should say, external memory sorting is, I've heard some reports that like 20 to 30% of computation is spent on sorting. So getting a really high performance sorting algorithm is really important. Okay. Now I also say that this is optimal for comparison sorts. Okay, you can't do better. And it's the same kind of information theoretic argument as you get for the lower bound for sorting in the standard computational model. Okay. The point is that there are n factorial possible orders of the items, right, as usual, which means that you need log of n factorial, which is about n log n, bits of information to decide which order is the sorted order for your items. Yes? And so the question is, what does reading one block tell you? Well, it tells you about what you're able to learn by reading those, that block is the position of the B block items among the M memory items. Okay? And I mean, we can assume that you already have the information about the M memory items and the B, they're sorted in memory, and that the B block items are sorted in their block. So what you learn is just how those B items land among the M items, which means that there are M plus B, choose B possibilities, right? Which of the M plus B possible positions among the combined items are occupied by the B items in your block? And that means that the log of this many, of this much, which is B log of M over B or so, bits of information are provided when you read a block. Okay. Except that in that block that you read, B log B bits are redundant info about the in-block order of the B items in the block. So instead of needing a true n log n bits of information, we only need n log n minus n over b times b log b bits of information, okay, which is just n log n over b bits of information to tell us what the total sort order is. So we need n log n over b bits of information. We get b log m over b bits of information each time we read a block. So that tells us that we must read n log n over b divided by b log m over b blocks in order to sort. Okay? So the same sort of information theoretic argument as for sequential sorting tells us that this minor change to merge sort gives us an optimal sorting algorithm. Any questions about that? All right. Well, I am going to ask a question because on the one hand, we've got B trees, and on the other hand, we've got this merge sort. Okay. And as I mentioned before, in sequential algorithms, a search tree can be used for sorting optimally, right? You can do an insert in log n time, and that means you can sort in n log n time. But there's something weird going on, which is that B trees, the search tree for external memory, cannot be used to sort optimally, right? As we saw over here, a B tree costs you n log base b of n, which is much worse than the running time we see over here, right? So this is an odd little mismatch, okay? If we look at the time for sorting, it suggests that we should be able to search in, well, 1 over n of the sorting time, right? 1 over b log base n over b divided by log base m over b, right? So what's wrong with that? Or, sorry, does that seem plausible? Does it seem like a plausible aspiration to be able to search that quickly? Yeah?
No, because that be less than 1 asymptotic.
Yeah, right? In fact, it almost certainly is less than 1, right? These are logarithmic terms, and b is quite large. So somehow, merge sort is kind of spending less than one search per, spending less than one search per, sorry, is doing the equivalent of searching faster than in constant time. Right? Which seems unreasonable. But that didn't stop the algorithmicists. They decided that they would figure out how to achieve this. Okay? And they realized that they kind of could. And what they recognized was what was limiting the B trees, right, again, was this fact that you were spending this log base b of n time on every single insertion and deletion. And this is just completely contrary to the way that external memory works, where you are reading and writing many things to and from disk at the same time. So they figured out a way to do that for searching was to do batching. Okay. They figured out that if you could sort of get a bunch of the searches accomplished at the same time, or get a bunch of the insertions into the B tree accomplished at the same time, then you could actually get them done at a cost of less than 1 per operation. Okay? And you pay the standard penalty for batching, which is latency. It may take a little while for you to get your answer, but they're able to get the throughput, the sort of number of operations that you can perform per unit time, very high to match what you can do with sorting. Okay, and this involves some pretty clever usage of external memory, so I wanted to show that to you. Okay. So the basic idea is going to focus on supporting inserts such that you can then traverse the result in order. actually, if this is all you had to do, then there would be an easy solution to this problem. Okay, if somebody told you, I'm going to give you n items to insert into the data structure, and then I want to be able to read them out in order, how would you provide for that very efficiently? Right, since this is the last lecture, I'm going right back to the first lecture. Right, what was our first principle? What should you do when the person gives you one item at a time to insert into the data structure? Yeah? Procrastinate. Just store it on disk, right? And then when they ask you to traverse, what should you do? How are you going to let them traverse the items in order if all you've done is stored them on disk? Yeah? Sort them, right? Problem solved, right? If I procrastinate on the end insertions and then sort, then the time is going to be exactly the sorting time. And so average cost per insertion is going to be what I want. Okay? And that works great for the basic idea, but it doesn't work so great if in reality they're going to be requesting an interleaving of insertions with lookups or traversals. Okay? So we're going to need to strengthen this approach to be able to do the lookups and the traversals in the middle of the insertions. Okay. The way we're going to do this is still it is still going to be procrastination focused. What we're going to do is we're going to keep a so-called buffer in memory until memory becomes full. And then we will sort and push that buffer to disk. Okay. And we are also going to keep a B tree, I put this in quotes, on disk. To receive the pushes. But again, in order to procrastinate, I am also going to put a buffer at each B tree node. So that if I am forced to push something out of memory, I don't have to push it all the way down to the leaves of the B tree. I'll just push it down one level. And that way, hopefully, I'll be able to collect more items at that node of the B tree before I have to do more work of pushing things down. The goal will always be to be pushing a huge number of items down the B tree at the same time so that the work of pushing each one is amortized. The block reads that I have to do to push them down is amortized over the many items that I push. Okay? And for this reason, because we structured it this way, these are called buffer trees. Okay. And you'll see in a minute why I call this why I put B tree in quotes. Sir? So up at the top, I've got my memory with its M items. Or rather, once I get to M items, I don't have room for any more items. I need to start evicting stuff. So I'm going to push all of that memory out into my B tree, or at least the first level of my B tree. And some stuff is going to go down to each of the children of that in-memory root. Okay? Now, how much work is it for me to push out all of the items in memory to the appropriate children. Well, that's very small. That's very well amortized, right? Because I'm pushing m items at once, and so I can afford to write whole blocks of items out to the various children of the data structure, right? So I'm only spending, right, since I'm writing b items in a single block write, I'm only spending 1 over b block writes per item that I push out, right? And that's exactly the 1 over b that I want in my search data structure, okay? Now, I might want to try to repeat this, right? I've pushed out some items from memory. They get pushed down into different children. Now maybe I've got some items in this child, and I'd like to push them down farther. The problem is, if only a few items got pushed to this child, I may no longer have enough items in the child to push things down another level. So that's why I keep a buffer here. I'm not going to push anything down from this node until there are so many items that, again, pushing down another level is amortized over the many items that I push down. Yes?
Could you explain again, like, the pushing down? So I can't really visualize the tree structure, right?
Well, so again, what you should visualize is essentially is a B tree, right? So we've got sort of, many children, and the keys are split according to the elements are split according to the keys in a particular node of the tree, right? And so when I'm inserting an item, at each step, what I have to ask is, which child does the item go into? And then I need to push it down into that item, into that child node. Right? And if I keep on pushing an item down, eventually it will arrive at a leaf of the B tree, and it'll be in the proper place.
How do I know that I only have M over B children?
I haven't yet told you how many children we have, and that's the next piece of this design. So I put B tree in quotes because we're actually going to use a much larger number of children in this data structure, again, in order to achieve that runtime. So the details here are that we're actually going to make the tree degree m over b. Why are we making the tree degree m over b? So that we can have a log m over b base, so that things can be log base m over b, right? That's going to be the depth of our data structure, is log base m over b of n over b. Okay. We're still going to put b items per leaf node. Okay. So that we can continue to think of this as a tree over blocks. Yes, a question.
What exactly is the buffer?
So what I'm going to do is, now that I have this notional tree, right, this tree of degree m over b, and that keeps branching out until there are only b items per leaf node, right? Now, with each node, I am going to keep where did it go? A buffer to receive up to m items pushed down from the parent node of the tree. Okay? So again, every item, when you insert it, it starts in memory, and then as various things fill up, it gets pushed down to an appropriate child, and it lands in a buffer. When that buffer gets full, then you're going to push those items down from that node to that node's children, and so forth. Did that answer your question? Okay. And so now the basic operation is going to be pushing an overflowing buffer down to the proper children. Now I am going to keep I am going to observe an invariant here. The overflow happens when some items arrive from the parent node of this buffer, or of this node. And I am going to keep an invariant that these elements coming from the parent arrive sorted. Okay? So from the perspective of a single node, every once in a while it gets this rain of items from its parent, and it can put them into the buffer if there's room. But at a certain point, it's going to get a rain of so many items that its buffer fills, and at that point, it's going to dump everything that it has in its buffer down to its children. Okay? But I'm going to rely on the fact that the items arrive from the parent sorted, because now I can think about the time for this basic operation. Okay. So how long does it take me to take whatever items I have in my own buffer, combine them with the sorted items that are arriving from my parent, and push them all out to my m over b children? Okay. So the first step is going to be to merge my buffer. Actually, that's not the first step. The second step is going to be to merge my buffer with the arriving items from the parent. Okay. Now, if I want to do a merge and keep things sort of, if I want to do that merge well, and have an easy time splitting things up among my children, the first thing I'm going to do is sort my buffer. Okay? Because if I sort my buffer and the stuff from my parent is also arriving sorted, now I have two sorted lists, and we know how to merge those very efficiently. Right? So how long does it take me to sort my buffer? Yes, a question.
If things are always coming in sorted, then can't we assume that our buffer is always sorted?
Unfortunately not, because we may get several different dumps of items, right? And so the first dump is sorted, but the second dump may consist of items that come before the items in the first dump. Okay. Yes? M. Each buffer is of size equal to your memory. So they're very big buffers. But they're very small compared to your external memory. And of course, you don't actually, you don't need to pre-allocate space for them, right? You'll only use as much space as you need for the items. So how long does it take me to sort m items that are stored on disk in my buffer? Yeah?
0.
Well, it's not 0 because I have to get them, right? I have to do the sorting in memory, and all these buffers are stored on disk. So what do I have to, so before I can sort them, I have to read them, right? Yeah? Yeah, and so all I have to do is read them, right? So sorting my buffer costs me m over b. Okay? Now, merging this buffer with the items that arrive from the parent, well, that depends on the number of items that arrive from the parent, right? So let's use k for that. And that's going to cost me m over b plus k over b, because the merge is linear. Okay. Now, I need to write the pieces of the buffer, of the sorted buffer, to the child buffers. How long does that take? Well, this is where we have to be a little bit careful. And this is also the reason for a lot of these strange parameters in the buffer trees. Right? I don't know how many items are going to each child. Some children might get only one item. But even if I store one item, even if I send one item to a child, I still have to do a whole block read and write, in order to add that item to the buffer for that child. Right? And so if I was sending one item to each child, that would be too expensive if I really want to be amortizing the cost of all of my rights to 1 over b. Okay? But because we have so many children and we're waiting until we have so many items, this cost is negligible. We are going to be writing at most one partial block per child, right? Plus the m over b plus k over b blocks that are full based on the number of items that are being pushed down. Okay? But since the number of, right, and so this at most one partial block per child, well, there's m over b children, so this is just another m over b blocks. Which means that the partial block writes that we may have to do are amortized again, or are dominated by the full block writes that we need to do. Which implies that the amortized cost to push down these items is order 1 over b per item. Okay? And this is the reason we made these buffers so big, right? We make these buffers huge so that by the time you're pushing items down, you can pay for all of the partial block writes that might be necessary in order to get everything out. Make sense? So now we're done, right? I've shown you that the cost of pushing items down is only 1 over b per item. And how many times does a single item get pushed down? Well, that's basically asking what is the depth of this data structure, right? So what is the depth of this data structure? Yeah? Exactly. And so that's the end, right? The total cost of all the pushdowns is n over b log base m over b of n over b. So pushing everything into this data structure costs you the same amount as sorting all of the items. Okay? But if all we wanted to do was insert, there wouldn't be any point to having this data structure. We would just collect everything, and then at the very end, we would sort it. Okay? But what we can do here is we can do queries as well. Okay. So to do queries, we simply insert, and to make this concrete, let's talk about predecessor queries. Okay. So to do predecessor queries, what we do is we insert the query as an item into the buffer tree. And we claim that when it arrives at a leaf, it will be next to the answer. And so that's how we do queries in this data structure. We insert them, and eventually they get answered, right? Because eventually that item gets pushed down to the leaf, and at that point it's next to the correct answer. Okay? Deletion is actually done similarly. What we do is we insert an anti-item into the data structure. And when it arrives at the same location as the item, they meet and annihilate each other. Okay? So again, we can't predict when this will happen, but we know that it will happen eventually. Okay? So what we have here is a data structure that has a very low cost per operation, but an unknown latency, right? It will eventually give the answer, but you can't say exactly when. Now, sometimes you might get impatient and decide you really need your answer. So the buffer tree also operates, or also offers, a flush operation. Which immediately empties all the buffers. So you can get your answers. Okay, and sorry, there's one other thing I want to get to, so I will leave it to you to fill in the details, which is essentially performing this analysis again to say that this doesn't change the amortized cost. It still turns out to be n over b log base m over b of n over b. Now, it has this cost. The cost of the flush is this, even if you're only, the amortized cost of the flush is this, even if you're only flushing one item. So you can't do the flushes very often, but you can use them as kind of a cleanup step to get all of the answers that you've been waiting for. Yes?
So you say flushing doesn't change amortized cost. Why don't we always flush?
Because that's what I just said. No matter how many items are, like if you flush on every insert, then you're going to be spending this much on every insert. Okay, so this is basically the cost of each flush, not the cost of all of the flushes together. Yeah? So flushing is essentially, yeah, it's basically saying I want to pay everything now so that I can get all of my answers now. The problem is that if you then decide to flush again 2 steps later, you're going to pay everything all over again. Okay. All right. So one more story I want to tell you, which is about a really sort of elegant approach to external memory algorithms that was invented right here in Charles Leiserson's group. But let's take our break first, and then we will resume.
My partner and I
Okay, we're going to resume, but I did want to take a quick, actually, maybe I'll do this online. After break, sorry, this is the end of the formal material of the class. There are a couple of more lectures that I think are pretty interesting on parallel algorithms, possibly some other stuff as well, which I can give if people are interested. Obviously, there won't be any homework on them. So since you are obviously the people who are most interested in actually attending lectures, I wanted to take a quick straw poll of who would be interested in getting a couple more lectures on parallel algorithms. These would not be on Fridays, probably a Monday. I might do Mondays only, or Monday or Wednesday, or something like that. And no, no pressure. I'm perfectly happy to not be lecturing. But if there is demand for this, I can put together a couple of these optional lectures. So who would be interested in hearing such a topic? Okay, that looks like a critical mass. I will figure out what dates make sense to do that and send out some announcements by email. Okay? Since this is also your last chance, are there any questions about the final project? Okay, remember that, sorry, is that a question? No?
The deadline is December 9th.
Sorry, what is, so the final day of classes, the last Wednesday is December, seriously? The last day of classes is December 8th?
December 9th, Thursday. The last day of which is Wednesday.
Wow. Okay, so December 6th then is the day that we will meet here for a peer editing of the final projects, and then they will be due on December 8th. Okay? Any other questions? Yes? What? Yes, it is. Okay. Yes, it is mandatory, well, primarily because everybody gets a better grade after their project gets peer edited. The projects always improve. And therefore, it is mandatory because we need peer editors to edit all of the projects. Right? So it's definitely a quid pro quo thing where you will benefit from it, and therefore I'm demanding some work from you as well. Yeah, I'll say a little bit more about this. When the projects are turned in, I will be looking, when you do the peer editing, you will send a short email to the authors and to me outlining the things that should be done to improve the work. And when I am grading, I will be looking at those peer editing suggestions and making sure that you did them. So, right, if a problem in your paper was flagged and you didn't fix it, that's a lot worse than a problem that nobody noticed. Okay? All right. So the last thing that I want to talk to you about is this really interesting concept called cache oblivious algorithms. So the external memory algorithms that we've looked at so far require the algorithm designer to fine-tune their algorithm to the parameters of the external memory. Okay? So you needed to know B, to know M, to know N, and based on those, you would set certain parameters in your data structure, like the number of children in your B tree, or the number of different subproblems you would merge in merge sort, right? And this is problematic for two reasons. One is that each time you move your system to a different machine, you have to retune the algorithms, right? You have to change all these parameters. You have to go find out how much memory does this machine have, and what's the block size, and so on and so forth. Now, what's even worse is that even on one machine, you might not be sure about the answers to these questions because of modern machines having a whole memory hierarchy. Okay. I talked about how you've got this fast memory and this fast internal memory and slow external memory. But in fact, on a modern machine, right, you've got what we do call external storage, the solid-state drives or whatever, right? And then you've got your RAM, and then you've got these caches, right? You've got your L1 cache, your L2 cache, and your L3 cache, okay? And when you start worrying about what is the bottleneck, what is the thing that is making my computer slow, it's almost certainly one of these levels, but which one it is really depends on the algorithm that you're running and the size of the data that you're working with. So for a while, Charles Isaacson's group worked on what they called self-tuning algorithms, which would run themselves and figure out where the bottlenecks are. But then they came up with a theory which is even more elegant, which is to design algorithms that achieve the external memory bounds without knowing the external memory parameters at all, just because of the way the algorithms run. You will know n because that's the problem size. You can tell what that is. All right? Just to show you a very simple example of this, right? How long does it take you to scan a contiguous array? Well, if you are using sort of the right kind of virtual memory, then when you want to scan an array, you just go through the items, the array entries one at a time. You look at item 1, item 2, item 3, item 4, item 5, so on and so forth, right? So you just read the virtual memory locations. And the OS fetches disk blocks as needed. When you read something from a disk block that you don't have. Okay? So if you scan n items that are contiguous in your virtual memory, how much work is the OS going to do fetching disk blocks? Well, it's just going to read those n over b disk blocks as you encounter them, right? So I can imagine that my virtual memory is actual memory, and I can just read things in it, and they'll be fetched, right? And the overall cost of doing that is just the n over b. Now, if I do random access, that's not true, right? If I just start randomly poking at different spots in my virtual memory, each of them may cause a disk block to be fetched. And as some disk blocks are fetched, the other ones that I'm going to need later might get evicted by my paging algorithm. And so I have to fetch them a second time the next time I read from them. So random access could get very expensive. But sequential scans are cache obliviously optimal for scanning through external memory. Make sense? So we kind of got that for free. But the question is, can we do this for real problems, for things beyond scanning? So let's go back to matrix multiplication, okay? Matrix addition, as we discussed before, is done just by scanning the two matrices. And so it is optimal in a cache oblivious setting as well, if you just run your standard algorithm for scanning and adding the two matrices. But we saw these challenges with matrix multiplication, right? And we used this submatrix layout, right? Where we broke the matrix into root m by root m submatrices, right? And that meant that our overall matrix consisted of an n over root m by n over root m matrix of these submatrices, right? And so the matrix multiply involved multiplying by submatrices n over root m cubed, by multiplying n over root m cubed pairs of submatrices, right? But each of the submatrix operations just required scanning in those two submatrices. So those all cost me m over b to read them in. And that meant that the overall cost was only n cubed over b root m. But in order to do that, I had to know m and b, or I at least had to know m, in order to know how to break out my submatrices, right? And again, even on a single processor, even on a single machine, I might not really know m, because is m the size of my memory, or is it the size of my L3 cache, or is it the size of my L1 cache, right? The bottlenecks could be in different places. Turns out that if you make this assumption about your OS fetching your pages for you as you need them, you can match this time bound without knowing m or b. Yes? So that is the approach of the self-tuning algorithms, right? But the problem is that what you learn about this particular scan may not continue to be true if you suddenly multiply bigger matrices, right? Maybe the matrices you're experimenting with fit into memory, and so your L3 cache was the bottleneck. Now, when you try and multiply some bigger matrices, all of a sudden RAM becomes the bottleneck and your parameters are wrong. Yeah?
Recursively, so that like eventually you're within block size?
Exactly. So the key idea behind cache oblivious algorithms is divide and conquer. Okay. So there's a very, sorry, a question?
Yeah, one more question about the problem specification. Are you essentially saying that m can vary throughout the course of the algorithm, or can, yeah?
No, in general, the assumption is that you are given one input instance and you want to be sort of instance optimal. You want to be sort of optimal for that instance, right? And that there is a single like the cache oblivious model doesn't even talk about the memory hierarchy. It just says there is this hidden m and this hidden b, and you want to be optimal to that m and b. Now, the way that plays out in the real world is that depending on your particular problem and your particular machine architecture, that may be, those may determine what the m or the b is. Okay? All right, so it's the simplest possible divide and conquer for matrix multiplication. If I want to multiply an n by n matrix, what I can do is break it into a 2 by 2 of matrices of half the size, and then do the submatrix multiplications, right? So if you think about it, I'll need to do 8 of them, because I've broken it up into a 2 by 2 matrix. And right, so here I'm just using n over 2 instead of square root of m for the submatrices, right? So in order to multiply two n by n matrices, I have to do 8 multiplications of n over 2 by n over 2 matrices. And then I need to do a bunch of addition, but adding matrices is just a scan, which is cache obliviously optimal. Okay. So does everybody buy this recursion? And what's the base case for this recursion going to be? Yeah?
M?
Exactly. And so again, this does not mean that your algorithm stops running. It just means that your algorithm stops paying anything for running, right? So once you get down to matrices of size m, the divide and conquer is going to continue, but all of the data will have been read into memory already, and you'll just be dividing and conquering in memory, which means that it's free. So the base case is going to be matrices of size root m by root m, which get drawn into memory, right? Or just root M. Right? And so if you solve that recurrence, you get exactly the bound that we got by careful construction before. Any questions about that? Okay, now I will say that this is actually not the best you can do. How many people have seen Strawson's algorithm? Right, so it turns out that this idea of divide and conquer for matrix multiplication, you can actually do a lot better than breaking it. I mean, you can break it up like this, but then you can actually get all of the subproducts that you need, not with 8 matrix products, but with 7. And this gives you a better than cubic runtime for your matrix products. And it essentially means that the faster matrix multiplication algorithms that we have in sequential land, in the standard computational model, they all actually turn out to be cache oblivious algorithms that work equally well in the external memory model. Okay? All right, so that was matrix multiplication. Let's look at the other things that we talked about. The next one was binary search trees, or search trees. So again, in designing an optimal external memory search tree, we said it's a good idea to make a branching factor of b, because that way each time you read in a block, you get the most possible information, and you subdivide the problem as much as possible from that one block read. But that requires that you know the block size. How might we be able to get past that without knowing the block size? Okay. And so here again, there's a divide and conquer insight. Okay. So in our B tree, if you think about it, what we did was we're searching for a key. So we read one block, and we search inside that block to find where that key lands inside the block, and that tells us which child we should go to, right? So I can generalize from that notion of searching in one block for B items and say that the problem of searching in N items can be subdivided as the problem of searching among D keys in the root. And then once I have searched among the D keys in the root, it breaks the problem down into a problem of size N over D for the next step of searching, right? And I could use any D that once I recognize that both the root step and the other step are instances of finding the position of a query in some keys, right? I can choose any degree that I want for this step. So when it's written this way, what's the natural choice for D? How do I balance these two terms? Square root of N, right? So essentially, in order to search among N items, I'm going to perform 2 different searches among square root of N items. Does that ring any bells? We did that actually a long time ago in data structures. Yeah? This was the Van M. de Bois data structure, right? And this leads to what is called the Van M. de Bois layout for trees. Okay. What we do is we say, we want to build a search tree on N items. What do? We make a search tree on root N items at the top, and then we have a bunch of search trees on root N items below. Okay. And we're going to lay out the data in memory in this form. So first we lay out the top, a tree for the root n splitters recursively. And then we lay out each of square root of n subtrees. Recursively. So this will be the first thing in memory, then this, then this, then this, and so on. But if we do this recursively, right, this first subtree is going to have a first, an upper part consisting of n to the 1/4 items, right, and then a bunch of little subtrees of size n to the 1/4. Okay? And we're going to keep going. And so where does this bottom out? Where do things get boring from the perspective of an external memory data structure? Is when you have a tree that holds b items, right? Because a tree of b items is going to fit into a single block of your memory. All right? So, you know, if you unroll the entire recursion, the very top b items of this entire search tree are what is going to appear in the very first block of this data structure. Right? And then the next b blocks are going to be the top b items of each of the child trees of this data, of this tree. Okay? So this also gives us the performance of our search. Right? What's the base case? It's what I just described. The base case here is when you get to b items, because they're all stored in a single block. So if you're going to stop when you get to b items, right, what is the depth of this recurrence? Right? You're taking repeated square roots until you get down to a size of b. Right? Another way to look at it is to say that as you're descending this tree, log b steps are going to stay inside of a single block of your search structure. Right? After log b steps, you'll get to the leaf of your current block, and it will lead you into a different block, where you will also descend log b steps. Right? Now, the total depth of the tree is log n, but you only need to read a new block every log b steps. So the number of blocks read is just log n divided by log b, which of course is equal to log base b of n. So simply laying out your data in this very clever way gives you the same search performance as a carefully designed B tree. Which I think is pretty cool. Right? Any questions about that? Yes?
Yes, I still don't get the point of half of Oblivious algorithm. So ultimately, you are going to bring into this base case where you realize that computation is free. But why don't you just first play around with your memory and see what you have to pay for the computation? Then you realize, oh, so.
Well, so again, there's a very interesting line of work on these self-tuning algorithms that basically do dry runs before they actually solve the problem. They spend some time testing their own environment. Okay? But the problem is that testing time, well, there's two ways you can do it. You can do it far in advance, right? You can install your software on a new architecture and then run a testing suite and discover what are B and M and use that to tune your algorithms, right? But for example, what if you're in a multitasking environment? Okay, so that many different processes are running at the same time on the machine, which means that the memory gets shared. Okay, so now it's not really about the physical memory anymore. It's about the amount of memory allocated to your process. And you have no idea what that is. So that sort of drives you to run your tests while you're running your algorithm. But if you're testing while you're running your algorithm, the cost of the testing becomes part of the cost of running your algorithm. And so you can't afford to test too much. Well, if you only test on small test cases, it might not tell you what happens when you run over your entire large input. Right? You might learn the wrong things about the bottlenecks. So you can do this, and again, there is a whole line of work on it, but not having to do it at all, right? Matching the performance of the optimal algorithms without ever finding out what your parameters are is a lot easier than trying to optimize for your specific case. Okay? All right, there's a little bit more in the notes if you want to read. We talked about linked lists, right? And it turns out that you can, if you design your linked list traversal algorithms properly, basically if you garbage collect as you're traversing, you can also get cache-oblivious linked lists whose performance matches the performance of our carefully designed linked lists. And buffer trees and all of this stuff has been ported to a cache-oblivious model. All right, keep an eye out for a sort of a schedule of when I'll talk to you about parallel algorithms. And aside from that, have a good rest of the semester. Remember to get your project proposals in. We'll try and turn them around very quickly so that you can get started right after Thanksgiving. And then I will see you, if not before, at the peer editing session on Monday.